Hi everyone, welcome to the lecture series in structural dynamics. The present topic is the logarithmic decrement for single degree freedom system. Now if you look at what happened during the undamped systems, undamped system continuously vibrating and the amplitude remains same throughout the vibration, which is undesirable. So when you add the damping in the system, then the amplitudes gets reduced gradually. So what is the rate of reduction in the amplitude? At what is the time when the amplitude gets reduced to the required level is the concern. So these things will be addressed as a part of logarithmic decrement. So by definition, the logarithmic decrement means it is the ratio of any two conjugative amplitudes to their logarithm. Because it's very fast rate decreasing, I need to take the logarithm. That's all. But what rate from the first amplitude to the next amplitude reducing is what is concerned. Since it is the very exponential decay, so I have to take a log. So log of x1 to x2 or log of x2 to x3 is the logarithmic decrement. Now the x1 becomes the first peak amplitude, x2 is the amplitude of vibration for the second peak, and so on. Now sometimes it may be not possible to find immediate or conjugative two amplitudes. So after some cycles, after n cycles, I may be able to find out the amplitudes. Initially it was some x1, and then after as 6 cycles or 7 cycles or n cycles, I have xn. So then the logarithmic decrement for that is delta equal to 1 by n ln of x1 by xn. So how to see the proof of this? So the proof, so now what we do, you take the response of single degree freedom system for a damped vibration, that is x is an amplitude, e power minus xi omega t cos omega t minus phi. So it has cos function, has some amplitude here. Okay, so now if at first peak that is x1, at time let us say t1, at time t1 I have x1, at time t2 I have x2, so on. So now if I try to plot this at every, let us say pi by w, that means your omega, that is a half a cycle, this is full cycle, then 1.5 cycle, 2 cycle, 2.5 cycle, and this is a 3 cycles. So if I try to plot, what happens? So initially something like this. So at a time t1, you can say, for example, this will be t1. My amplitude of the vibration is x1. Then from this point to this point, I have a complete td. So total time for the second peak is t1 plus td. So at t1 plus td, I have amplitude of x2. At t1, I have amplitude of x1. Okay. Now this is how my amplitude getting reducing here. So this is called exponential decay. So I will call decay is written as here e to the power minus xi omega nt. Okay, t1 plus td is the second peak. So this is a logarithmic decrement, it is decreasing in the exponentially. Now, if you look at x1 is amplitude at the first peak, x2 is amplitude at the second peak, and that is the time t2 is equal to t1 plus td. So if I substitute into the response, the total amplitude into this e to the power minus j omega t, that is the first. The second, x of t2 will be x, because this amplitude remains same. This is a term only changing to me. This is only changing, the amplitude remains same. Okay? That's why the x's remains same. The only difference is this e power minus j omega t1, this one. So if I take the ratio of x1 by x2 or x of t1 by x of t2, so x e to the power of minus j t1 and this, then x get cancelled out. Then, and this, if I separate this e power j omega t1 and this get cancelled out. So I left with only e power minus j omega t. So if I take this reverse, so it will go to e power minus become plus j omega td, and to find out this I have to take a natural log. So natural log of x1 by x2 becomes, this will simply becomes j omega td, and we know that t omega is j into under root of 1 minus omega into under root of 1 minus a square, and also td equal to 2 pi by omega t. Substituting this td into here, so what I get, that ln of x1 by x2 is equal to, that is nothing but my logarithmic decrement, which is delta j omega td, that is td substituting 2 pi by omega t, and omega t is omega into under root of 1 minus a square, this. So this is my logarithmic decrement and damping ratio relation. If the j is sufficiently large, I have to use this equation. If j is very less, let us say less than 10%, so I can approximate the equation as j equal to delta by 2 pi. This is quite sufficient to find out the damping ratio in a given system. Okay, so this, if j is less than 10%, let us say 0.1, square of that is 0.001, 1 minus 0.001 is 0.995 or 991. So this is all, under root of that will be 0.998 something. It's very close to 1. That is why I can neglect the term, taking it to be 1. So j will be equal to delta by 2 pi. So let us look at one numerical on this damping logarithmic decrement, how to find damping ratio in a given system. So there is numerical here is a displacement time plot of a single degree freedom system. Free vibration gives a displacement of 7.5 millimeter at time t1 and 1 millimeter after 7 cycles. Determine the logarithmic decrement and damping ratio. So the first displacement is given as 7.5, right? So x1 is 7.5 millimeter. Then after 7 cycles, n cycles is 1 millimeter. So the n becomes 7 cycles. Then as per the logarithmic decrement expression, 1 by n ln x1 by xn. So substituting here 1 by 7 and starting from 7.5 going to the 1, so I get delta 0.28. So this is 2 and less delta logarithmic decrement. If it is something around 1 or even more than 1, this delta, then I can say it is damping ratio is very high, but since it is quite low, I can neglect this term, denominator term, take it as a 1. Okay. Then substitute delta is 0.28 by 2 pi, I get 0.0458 or 4.5%. So this 4.5% is only to express your damping ratio. So this is 4.5%, but whenever write the damping ratio, we'll write 0.0458. But while telling, we can say 4.5%. So let us look at another numerical. A single degree freedom system, a frame, mass of 5000 kg and lateral stiffness of 4 into 10 power of 6 Newton per meter. It has got damping ratio of 4%. Now we need to find out the natural frequency of damped and undamped. If the frame is displaced by 25 millimeter and released suddenly, that is what initial displacement. We need to find out the peak displacement of first 5 cycles. First cycle, what is the peak? Second cycle peak, third cycle peak, like this 5 peaks we have to find out. So let us see how to solve this. So we have K equal to 4 into 10 power 6 Newton per meter and mass as 5000 kg and damping ratio of 4%. The undamped natural frequency is root over K by M. This is asking first undamped natural frequency. So we substitute this and get a undamped natural frequency as 28.28 per second. Now let us say damped. So damped means omega d. We know this damping ratio is given as 4%. It's very less. So directly I can understand that omega d is omega n are same, because 1 minus z square term becomes almost close to under root of 1 minus z square term becomes almost close to 1. But still we can find out here 28.25, 28.28. So very close. This is damped frequency. Now he is asking find out the peaks. So now using peaks, different peaks means we have to go by logarithmic decrement. So logarithmic decrement formula delta equal to 2 pi into xi. We don't take the denominator term because our damping ratio is very less, 4%. So by substituting here, so I get logarithmic decrement as 0.25. I also have the formula for logarithmic decrement is delta ln x0 by x1. The initial displacement given as 25 millimeter. So we are supposed to find out the first peak x1. So substituting here 0.25 equal to ln 25 by x1. So now taking the antilog, the 25 by x1 becomes e to the power 0.25 and I can get a value of x1 is 19.47. Similarly, the second peak x2, again delta equal to ln of x1 by x2. Since I already got x1 here, x1 is already there with me, so I can find out x2. Same method, that is 19.47 by x2 equal to 0.25, then taking antilog. Similarly, third peak displacement x3, same formula delta equal to ln of x2 by x3. Now x2 is obtained here 15.116. Substituting here I can get x3 as 11.8. Then fourth peak displacement x4, same delta equal to ln by x3 by x4. By substituting x3 equal to 11.8, so I can find out the x4. This is x4 9.18, and fifth peak displacement x5, so delta equal to ln by x4 by x5. I know x4 which is 9.18, x5 can be found out as 7.14. So like this I will be able to find out all the peaks. Thank you.